for rational functions. So section 3.5, rational functions. Let's recall, a rational function, r of x, is just a ratio of two polynomial functions, p of x and q of x. And so these are rational functions in some field, f, with some indeterminate x. And I assume I'm not dividing by 0, so I assume that q of x is not 0. Recall that the domain of my rational function r, the domain of p, intersect the domain of q, without the kernel of q. And well, usually the domain of a polynomial is everything. And so this is usually all real numbers. And you just get rid of the domain of q, the kernel of q. The kernel of q is the set of all x in the domain of q, such that any don't divide by 0. So the domain of a rational function is usually all real numbers except when you're dividing by 0. Asymptotic behavior. So we mentioned asymptotic behavior previously, but we didn't really go into it very deeply. Here we'll have to talk a little bit more about asymptotic behavior. So G is asymptotic to F near A, which is a real number, or it could even be plus or minus infinity, if F divided by G approaches 1 as X approaches A. So again, A could be a real number or plus or minus infinity. Now, we have some special names for things. Actually, a vertical asymptote really is not a function, but for concepts that are similar to what we had for asymptotic behavior. So a vertical asymptote. F of x has a vertical asymptote at x equal a if f of x approaches either plus infinity or minus infinity as x approaches a. Oh, I didn't say what the horizontal asymptote was. The horizontal asymptote is an asymptote such that you approach equals some constant. So let's find the equations of the vertical and horizontal asymptotes of each graph. Also find the domain and range. Okay, so for problem number 12, it looks like this. So let's first find the vertical asymptote. And again, we're just looking at the graph, so notations here. So visually, what's a vertical asymptote? Well, it's these lines. So it is the line that you approach, the vertical line that you approach as x approaches some value. And so in this case, it is the line x equals 2 and the line x equal -2. You must write it as a vertical line. A vertical asymptote is a vertical line. So you must write the equation of a vertical line. Why is it misspelled? Asymptote. So a horizontal, just like a vertical asymptote was a vertical line, a horizontal asymptote is a horizontal line. Well, what horizontal line do these approach as x goes to either plus infinity or minus infinity? Well, it approaches the x-axis. And so it approaches the horizontal line, y equals 0. Let me do, well, actually I don't need a whole new page. I can just move this down a little bit. Next, I want to find the domain of my function. So the domain of my function is, well, if I look along this x-axis, for what x-axis do I have a corresponding y value? Are there any x values that don't have a corresponding y value? Well, it's all real numbers have a corresponding y value, except when x is -2 or when x is +2 at the vertical asymptotes. So the domain is the set of all, the domain of my function. I don't know if is the set of all x not equal to ±2. It is the union -infinity to -2, union -2 to 2, union 2 to infinity. And that is the domain of my function. Let's determine the range of my function. And so the range
Excuse me.
Yes, question.
I have a question about the answer this one, because when I, no, that the domain, it's about domain.
Okay.
The final answer,
Mm-hmm.
you use 3 of them. It's minus infinity and -2.
Mm-hmm.
And here we have the -2 and +2.
Yes.
If we didn't write this one in the answer, why is wrong? Because here we have the sign here. It's mentioned is not -2, and here it's not +2.
That's right.
Why
So
we?
that's right. So it's not -2 nor +2. Therefore, there are 3 intervals. This first interval, this second interval, and this third interval.
Oh, we have to show the 3 interval.
That's right.
Okay.
Because if you remove 2 things from a line, you actually get 3 pieces.
Yeah.
So it's always one more piece than what you take away.
Yeah.
And that's geometry.
Yeah, that was. Thank you. Thank you so
Okay,
much.
okay. But good question, right? Okay, so the range. So in this case, the range are the y values. So y values. And so if I look here, well, we have a y value for each of these points, actually everywhere. And so if I took any y value, I could find a corresponding x value, which would give me that y value. So no matter where I look, there's always at least one y value. And so notice that this, even though it doesn't look like it, this actually intersects the x-axis here at the origin. So the y-axis here at the origin. So for any value of y, there corresponded an x value that gave you that y value. So the range is actually everything. So the range is all numbers. And that is your answer. Okay. Let me do problem 22. I'll definitely need a page. Find the domain of each rational function. Do not graph. So the domain of a rational function is, well, the domain of the numerator, domain of the denominator. Domain of the numerator is everything, domain of the denominator is everything, minus the kernel. Meaning, to find the domain of a rational function, all you have to do is set the denominator to 0 and solve for x. So the domain will be everything except when I divide by 0. So everything except when x plus 3 is 0. So everything except for 3, negative 3. And so the domain of f is everything except for negative 3. It is negative infinity to negative 3, union negative 3 to infinity. And that is your domain. Okay. Let me do problem 32. We might be able to move that whole thing down. Okay, there it is. So let's move this up for 1 second. Find the vertical asymptotes, if any. Oh, again, we don't need to graph yet. We're just doing some. Okay, moving. Okay, so close enough. So this is problem number 32. So, and let me get rid of this for 1 second. Delete. So I have a little bit more space. Okay, find the vertical asymptotes, if any, of each rational function. Do not graph the function. This will be slightly different. Okay, so if I was trying to find the domain, I would set the denominator to 0. If I want to determine a vertical asymptote, I have to be a little bit more careful. First, let's factor both the numerator and denominator. Now, let me cancel. I can cancel out the x minus 4s. So if I do that, I have f of x is equal to 1 over x plus 4. If, and maybe I'll put this in red, if x is not equal to 4. 4 will not mean your domain. It'll actually be a hole. There's actually going to be a hole when x equals 4. But we don't care. It's not a vertical asymptote. So now after I've simplified, I can now find my vertical asymptotes. Set denominator 0. So x is equal to -4. So this is my vertical asymptote. So note that if you set originally the function, the denominator for the function equal to 0, you would actually get an incorrect answer because x equaling 4 is actually not a vertical asymptote. It has a hole when x is equal to 4. So we have to be a little bit more careful for that. Let me do problem number 41. Find the horizontal asymptote. Do not graph the function. Okay. So let's do that. Find the horizontal asymptotes, if any, of each rational function. Do not graph the function. Okay. So I can state this several different ways. So let me do this more than one way. Horizontal asymptote. If I look at the degree of the numerator, the degree of the numerator is 1. That's the power of x is 1. The degree of the denominator is 3. Since the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is just y equals 0. Okay? So we can just look at the degrees of the numerator and denominator and straight off the bat say, oh, okay, that's going to be y equals 0. Is larger than degree of the denominator, then there is no horizontal asymptote. There's going to be some other asymptotic behavior. If the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote would just be the ratio of the leading order coefficients for the numerator and denominator. Let me look at this a different way. Let's look at asymptotic behavior. And this will give me also the horizontal asymptote. Okay, so get another page here. So let's look what happens as x gets large. So as either x goes to plus infinity or minus infinity. So I'm looking at as the absolute value of x goes to infinity. Well, x, and let's write it this way, x plus 1 over x cubed minus 4x. And we use this little squiggly to say that's asymptotic behavior. It's asymptotic too. Well, if x is very large, adding 1 to, if you have a billion and you add 1, it's still pretty close to a billion. Similarly, x cubed is much, much larger larger than 4x. And x cubed minus 4 are pretty close to each other if x is very large. And so we have that x plus 1 is asymptotic to x over x cubed. So f of x is asymptotic to 1 over x squared. I can cancel out x in the numerator and denominator to get 1 over x squared. As x gets very large. But you notice that 1 over x squared, well, as x gets very large, 1 over x squared gets very, very small. And so this says that y equaling that as x goes to infinity, y approaches 0. So therefore, y equaling 0 is the horizontal asymptote. And we actually found something nicer than that. We found that it actually looks like 1 over x squared for very large values of x. So we actually have determined what it looked like for large values of x. Okay, let's do the next problem. I'll probably bring that whole thing up. Find this slant asymptote. Sometimes called the oblique asymptote. Find the slant asymptote, if any, of each rational function. Do not graph the function. Okay, so what you notice here is that this function here does not have a horizontal asymptote because the degree of the numerator is bigger than the degree of the denominator. And so it approaches, as x gets large, y approaches infinity. So it doesn't approach some finite value. So let's try to first simplify this rational function. And so let's divide this numerator by the denominator. I'm dividing by x minus 4, so let's use synthesion. It'll be easier. So I have 2x squared minus 5x plus 1. Let's drop down to 2 times 4 is 8, minus 5 is 3, times 4 is 12, plus 1 is 13. Okay, so we get that f of x is equal to 2x plus 3 plus 13 over x minus 2. X minus 4. Okay. And so I've just rewritten my function to look in a nicer form. But now notice when we're looking at horizontal asymptotes, oblique asymptotes, slant asymptotes, we're looking at what happens as x goes to infinity. Well, what we notice is that as x goes to infinity, this term goes to 0 as x goes to infinity. And so this other part doesn't go to 0, and we call that the slant asymptote. So my slant asymptote is just y equals 2x plus 3. Notice that the other part is my vertical asymptote. And so as x goes to 4, this other part tells me what the function should look like near x equals 4. It looks like 8, 11 plus 13 over x minus 4 near 4. Okay, let's do problem number 60. Find all vertical, horizontal, slant asymptotes, x, y intercepts, symmetries, and then graph each function. Check your work with a graphing calculator. Oh, okay. So actually, let's see if I can pull up my graphing calculator. There it is. Okay, so let's do this. So first, before I even start to sketch the graph of this, let me factor both the numerator and denominator. Please get out of the way. Okay, thank you. So this is the difference of squares. So this factors into x minus 2 times x plus 2. And this is also difference squares. X minus 3, x plus 3. So that's what my function looks like. Okay. Voila. There's my other. Try to get me back. Okay, so first things to note is that I'm not doing any sort of cancellation here. So there's no holes in my graph. Okay. Next, I probably drew it here because I like the sketch of that. I like the way I sketched it. Okay, so let me add another page here. Okay, so let's look for vertical and horizontal asymptotes, if there are any. So vertical asymptotes. Since I already checked that there are no holes, there's no way to sort of cancel things out. To find my vertical asymptotes, I just set the denominator to 0 and solve for x. So I'll set each factor to 0 and solve for x. So in this case, I'm going to have two vertical asymptotes. Trying to get back my, there it is. So add 3 to both sides. Subtract 3 from both sides. So I have vertical asymptotes at x equal positive 3 and x equal negative 3. Now let's look for horizontal asymptotes, if any. So I have here y equals x squared minus 4 over x squared minus 9. So let's look at the asymptotic behavior as x goes to x squared. And x squared minus 9 is pretty close to x squared, 4 values of x that are extremely large. Okay. So I can cancel. And so I can cancel this, get a 1, 1. So y is asymptotic to 1 as x approaches infinity. Therefore, the horizontal asymptote is just y equals 1. Okay. Let's try to find intercepts. Let's say the x-intercepts. So let's set the numerator to 0 and solve for x. So x minus 2 is equal to 0, or x plus 2 is equal to 0. So x is equal to 2, or x is equal to negative 2. Do not just sort of say that, oh, the x-intercept is x equal to vertical asymptotes and all that. So x equaling 2 would imply that that's an equation of a vertical line, which it isn't. So the x-intercept is at 2, 0 and at negative 2, 0. These are points on the graph. Okay. Now let's find the y-intercepts. I guess I need another page. The y-intercept, which in this case is not going to be very useful. So to find the y-intercept, replace x by 0 and solve. 0 minus 4 is a negative 4 over negative 9 is positive 4 over 9. And so my y-intercept is at 0, 4 ninths. Okay. So we could do some asymptotic behavior, but this is probably enough for this graph at least to sketch it. So we have here 4 over 9? Really? Okay, well, we're a little bit above it, but doesn't matter. Okay, so we have vertical asymptotes at plus or minus 3. Oh, the asymptotes are plus or minus 3. I thought there were 2. Yeah, they were plus or minus 3. Okay, so we do not have any holes. The stop. The horizontal asymptote is y equal 1. The vertical asymptotes are at x equal 3 and x equal negative 3. The only x-intercepts are at plus or minus 2. There are no holes in this graph, and the y-intercept is at 4/9. So let me actually make this a little bit nicer. Is at 4/9. So actually it's a little flatter than what I drew here. So it's, yeah, whatever. So this is at 4/9. Okay. Um, so let's sketch the graph of this. So we go, oh boy, we have a x-intercepts at plus or minus 2 and a y-intercept at 4/9. So we have to go through these 3 points. We can't cross the x-axis any other place. There's a barrier here at 3, so we've got to go to infinity when we approach plus or minus 3. So this graph has to look something like this. Next, we have to approach at infinity the horizontal line y equal 1, and we have to treat x equaling 3 as a barrier. We can't go past it. We can't cross the x-axis because we can only cross the x-axis at plus or minus 2. So we can't be below this. We can't approach 3 by going below the x-axis, because if we did, we'd be crossing the x-axis for either of these. So therefore, we must be above the x-axis, approach plus, or, well, in this case, minus 3, and y equal 1. So the graph should look something like this. Oh, and I guess I should also say, for symmetry, is symmetric about, it's an even function, so it's symmetric y-axis. And the reason for that is, if I looked at, okay, come on. If I looked here, I have to actually do a little bit more. If I replace x by negative x, I'll get a negative x squared minus 4 over negative x squared minus 9 is x squared minus 4 over x squared minus 9, which is f of x. And so this says that it's symmetric about the y-axis. It is, let's pull that down. It is an even function. We could have seen that it was an even function by just noticing the powers here are 2 is even, x to the 0 is even, 2 is even, x to the 0 is 2 and 0, they're all even. Therefore, this is an even function. Therefore, it's symmetric about the x-axis, about the y-axis. So this here should look the same as on the other side. And it does look symmetric. Okay, let's do problem number 78. With the same, all the same instructions. Basically, do everything. So f of x factor out an x. What remains is x squared minus 2x plus 1, x minus 2, x plus 2. Since this is a difference of squares, so by the special product formula, you have that. So this is equal to factor. So this is a monoquadratic trinomial. So this factor is x. We bring down the minus times plus is minus. I want two whole numbers whose product is 1 and whose sum is 2. So 1 and 1 over x minus 2 as follows. X times x minus 1 squared over x minus 2, x plus 2. Okay, good. So now we notice that, well, I'm not able to cancel anything, so there are no holes. Now let's look for asymptotes. So let me look for the vertical asymptotes. So I'll set the denominator to 0. X minus 2, x plus 2 equals 0. So the fact that this is a integral domain, a polynomial over integral domain is integral domain. Add 2 to both sides of your equation. Subtract 2 from both sides of my equation. And so these are my vertical asymptotes. Let's look for horizontal asymptotes, if any. Well, my function, the degree of my numerator is 3, and the degree of my denominator is 2. And so since the degree of my numerator is greater than the degree of my denominator, then there is no horizontal asymptote. So I better start looking for other asymptotes. Okay. Okay, so let's do some asymptotic behavior. So I have f of x. We simplified it to look in the form x Actually, let's do it in the unsimplified form. I had it equal to x cubed minus 2x plus x, 2x squared, plus x over x squared minus 4. So let's divide this, okay? Oh, and maybe I'll write it as x minus 2, x plus 2. And so let's divide this. And so first, I'll do division by x minus 2. So this is 1x cubed minus 2x squared plus x plus 0. Okay, so drop down the 1 times 2 is 2. Plus minus 2 is 0 times 2 is 0. This gives me a 1 times 2 is 2. Okay, next, let's do minus 2. So let's drop down the 1 times minus 2 is minus 2. Plus 0 is minus 2 times 2 gives me a 4. Plus 1 is 5. And let's do minus 2 times 5 is minus 10. Plus 2 is minus 8. Okay, so let's write this. So I have that f of x can be written as follows, as x minus 2 plus 5x minus 8 over the x minus 2 times x plus 2. So let's just write this as x squared minus 4. And that's what your, if you divide these two out, you can simplify this as. Okay, so let's do some asymptotic behavior. First off, I guess, as x goes to infinity, this term goes to 0 as x goes to infinity. And so my oblique asymptote, or slant asymptote, actually I forget which one they called it. I think they called it a slant asymptote. Is just going to be y equal x minus 2. It's that first part. Since the latter part becomes negligible, large. Okay. Okay. Let me do some further sort of asymptotic behavior. as x approaches, say, 2. So near x equal 2, well, you get a 2 minus 2 plus 5 times 2 minus 8 over, well, if you plug in a 2 here, you get infinity. So I'll just say, and let me write this as x minus 2 times x plus 2. So as x goes to 2, f of x goes to, well, 2 minus 2 is just 0. 10 minus 8 is 2. 2 plus 2 is 4. X minus 2. And so I can cancel out 4 divided by 2 is 2. And so f of x is asymptotic to 1 over 2x minus 2 as x approaches 2. Let's look at what happens as x approaches negative 2. Your other asymptote. So this is what happens near the vertical asymptote. Let's look what happens near the other vertical asymptote. So f of x is, well, very similar to x minus 2 plus 5 times x minus 8 over x minus 2 times x plus 2. Okay, so let me get a little more room here. So f of x here approaches negative 2 minus 2 is negative 4. Minus 10 minus 8 is minus 18. Minus 2 is a minus 4, x plus 2. And so I can cancel. So I get 9 over 2. So f of x approaches negative 4 plus 9 over 2 x plus 2 as x gets close to negative 2. Okay. Let's see what happens at infinity. Oh, well, we already did infinities. We already did the infinities. That's this Latin asymptote. Okay.
Excuse me.
Yes.
In the middle of this, if you go back from here, here, as a x2, I don't understand here.
Mm-hmm.
The denominator, we put here the x equal to.
Yes. So
But
I replace x equal 2 everywhere except when I divide by 0. If I plugged in x equaling 2 and I divide by 0, I don't put in 2, I just leave in x. So if I look here,
because you don't want the denominator
divide by 0.
0. Okay.
Yes. So that's the rule. The rule is wherever I see an x, I replace x by whatever I'm approaching, except if I'm dividing by 0, in which case just keep the x.
Okay. Okay.
That'll
Thank you.
give you the asymptotic behavior. So that's the rule. Okay?
Okay. Thank you.
Okay. So that's it. Oh, and the only other thing is I didn't do the intercepts. So let's do the intercepts, x-intercepts. Okay, so to find the x-intercepts, I'll set the numerator to 0. Because obviously the denominator cannot be 0 in order for you to have a x-intercept. Set each factor to 0. Solve for x. So the x-intercepts are at the origin and at 1, 0, which is a double root. And actually, I should actually important. So this is a double root. Maybe I'll do that in red. And so actually I should have, well, so what that means is that near x equal 1, something will happen. So maybe I should have looked at some asymptotic behavior at near x equal 1 and x equals 0 to see what the roots do near those. So let's do some further asymptotic behavior. Near the roots. So f of x. So this is, let's say, as x approaches 0. See what happens. So f of x would be asymptotic to 0 minus 2 over. So at 1, it's not going to do that much. Plus x. In this case, I want to see what happens near x equals 1, x equals 0. Okay, so x, and this would be 5x minus 8 over x minus 4. Okay, so we're making x small. So f of x is asymptotic to x minus 2 plus, I'm divided by 4, so it's by negative 4. So this is plus negative 5 over 4x plus 2. 2's cancel. So f of x is asymptotic to a negative 1/4 x as x is close to 0. So as x is close to 0, it should look something like that. Next, we want x equal 1. So what happens near x equal 1? as x approaches 1, what happens? So f of x is very close to, well, for x near 1, this is going to be oh, actually, maybe I should. Let's just use the original form for my function. So let's just use this form here. The x times x minus 1 squared. Let's use that. Oh, at 0, I could have used that too. Would have been easier. Actually, I should do that. Even though I'll get the same answer. Let me stop. Let me go back for a second. I get the same answer, but it'll look a little nicer. So let me use instead the original, which looked like x times x minus 1 squared over x minus 2 minus x squared. Okay, come on. So this is x minus 1 squared over x squared minus 4. Okay, so let's use that instead. Okay, so as x goes to 0, well, so this will just be negative 1 squared, which is 1, divided by negative 4, which gives you what I had from before. That f of x, that's a little cleaner. F of x approaches negative 1/4 x as x goes to 0. Now let's do this. As x approaches 1, well, x approaches 1. X minus 1, well, I'll just leave it as x minus 1 squared over 1 squared minus 4. There. And so 1 minus 4 is just 3. So f of x is asymptotic to negative 1/3 x minus 1 squared as x approaches 1. Okay, so now let's sketch a graph of this. Did I do my y-intercept? No, I didn't do my y-intercept. My y-intercept, of course, will just be the origin. So last thing is y-intercept. It's the only thing I didn't do. So, and then I'll sketch a graph. So the y-intercept found by setting x equal to 0, 0, 0 minus 1 squared over 0 squared minus 4 is 0. So again, we're at the origin. Okay, so let's try to sketch a graph of this, if I can. I hope I have enough space. Okay, so let's see, 1, 2. Vertical asymptotes are at 2. So here are my vertical asymptotes. -2 and +2. No horizontal asymptote, but there is a slant asymptote. Oh, there's no way I can draw this because it's got to go way down there. Okay, so delete, new page. There's no way I can sketch a graph of this without doing a whole page. Okay. Let's try to sketch this thing. Okay. Oh, I didn't look at symmetry. So I have a little space there to do symmetries. I don't think it has any symmetries. This is, it has no symmetries. So symmetry. That is going to be none. So f of -x equals -x -x minus 1 squared over -x squared minus 4. So this is equal to a minus x plus 1 squared over x squared minus 4. Well, the x squared minus 4 looks good. The minus is okay, but I have a plus here. So this is not equal to f of x, or so this is not equal to f of x, not equal to, or maybe I'll just say, so this is not equal to f of x. This is not equal to minus f of x. So it's not symmetric about the origin. It's neither even nor odd. Not symmetric about the origin, not symmetric about the y-axis. It's a function, so it's not symmetric about the x-axis. So this has no symmetries. Okay. Good. So now let's do 2. Okay, so I have here my vertical asymptotes. Okay, I have here x minus 2. Even at that, it's going to be hard to sketch it. Okay, so this is a slant asymptote, the graph of y equal x minus 2. Okay. We pass through the origin and 1. Okay. So we have to approach this here and this here. So, and we don't cross the x-axis anywhere. And we have to approach these. So in this region, we have to look something like this. And like this. And this is the graph of y equaling x cubed minus 2x squared plus x over x squared minus 4. Now, in this region here, well, at 1, it looks like at 1, it looked like a negative 1/3 x minus, looks something relatively flat like this. And then through here, it looked like a linear sort of. And so it has to look like this, approach this, go through this, look like a parabola here, go down and approach this. And that's what the graph looks like. So it has to approach these asymptotes here. And I actually said, if you look at the asymptotic behavior, exactly how it approaches each of these, where at -2, well, at -2, it looked like some translation of some positive 1 over x plus 2. So that looks like this. And for x going to +2, it looks like some positive factor of 1 over x minus 2. So again, it looks like this here. So that's what the sketch of the graph looks like. Okay, let's do problem number 82. Graph each rational function. Note the numerator and denominator of the fraction share a common factor. Oh, which means there's going to be a hole. So first, factor, x squared. What remains is x minus 1 over x minus 1. So I can cancel. Oops. But when I cancel, I have to note that I've actually created a hole. So this is equal to x squared if x is not equal to 1. So these are equal to each other when x is not equal to 1, but when x is equal to 1, obviously 1 squared is 1, whereas this is not defined at 1. So there's actually a hole when x equals 1. So let's try to determine the location of the hole in my graph. So it's a hole when x equals 1. So let's figure out what that hole is. So f at 1 is 1 squared. And so the hole is just at 1, 1. So this is a hole. The graph of y equal x squared is pretty easy. So I'll just sketch the graph of y equal x squared. And I don't need anything large here. The graph of y equal x squared just looks like this. But it says that we have a hole at 1, 1. So I'm going to put a little hole here. So the graph looks like the graph of y equal x squared. The only difference is that there's a little hole here at the point 1, 1. And that's what the sketch of the graph looks like. So that finishes off section 3.5. Let me go on